so much fun. Excellent presentation. Oh, thank you.
From Institute of Astrophysics in Paris and University of Sorbonne. We will be talking about more quantitative take on the Drake equation and also its connections with Fermi paradox. And without further ado, we can start.
Thanks a lot, Jan. So, I am from the Institute of Astrophysics in Paris. I spent more than 40 years of my career there. I have done a little work on the Fermi paradox and its link to the Drake equation, but my main field of interest of research is stellar and galactic astrophysics. I am a modelist of stellar interiors and especially the Milky Way. I will start with a short historical introduction because it's always very interesting to know that the questions we are asking today, in some cases, they are very old questions, and simply we have more tools to tackle them. I will start, I'm of Greek origin, so it's always when we are discussing about historical ideas and principles, we go back to the ancient Greeks. And so, in the ancient times, this topic has occupied a lot the thinkers of that period. It was known as the plurality of the worlds. It's not known about extraterrestrial intelligence, but the plurality of worlds. And there were basically two currents of thought. One of them was the atomist current. The atomists, Lefkippus, Democritus, were thinking that the world is made of atoms, and there are an infinity of atoms in the universe, and their combinations make what we see around us. And since there is infinity of atoms and infinity of combinations, there should be also an infinite number of worlds. The argument is mostly presented with this. Metrodorus was a disciple of Democritus, and he said that consider the Earth as the only populated world in infinite space is as absurd as to assert that an entire field sown with millet, only one grain will show. It is basically this argument that proponents of extraterrestrial intelligence are using today. The universe is large. Nowadays, we know that our galaxy is quite large, 100 billion stars. So, it would become strange, absurd, to think that there is one inhabitable world. But this was not the opinion of the two greatest thinkers of Greek antiquity, of Plato and Aristotle. They believed there is only one world, and their argument was based on the physics of the Aristotelian universe. It's not only that the Earth was on the center of the world, that's one thing, but basically the physics of Aristotle. Because Aristotle thought that below the orbit of the moon, the world is made of the combination of the four basic elements: the earth, the water, fire, air, and the world of this combination, these elements are perishable. And their combinations are also changeable. They change in time. They don't. Whether the world above the orbit of the moon, the world of the sun, and the stars, and the planets, was made from a different stuff, from the ether, the fifth essence. I don't know if you have seen the movie, The Fifth Essence, with Bruce Willis. But this was the ether for the ancient people. And the ether was a perfect element, unchangeable. So there would be no change up there. And this means there is a possible to have other worlds up there. By the way, Democritus, who is an extraordinary thinker, he was, of course, the father of the atomic theory. He didn't write a lot, but we have found some of his writings. And this is what is attributed to Hippolytus, who wrote about Democritus. And Democritus said there was an infinite number of worlds of various sizes. Some of them do not have a sun or a moon, while others have a sun and a moon that are larger than ours. And others have more suns and moons than what we have. And he further said, some worlds are inhabited by living creatures and have no plants or moisture. These look amazing with respect to what we know today. But, of course, no one could think that Democritus had some extra sensorial perception of science and knowledge. He did not have it. And remember what I said, the topic was the plurality of worlds. What the ancient Greeks had in mind by saying a world is what a simple person would think of a world. If you stay on this earth, you look around you and you see the sun, the sun in daytime and the moon and the stars at night time. This is a world. So these people thought, when they said other worlds, they thought that further away, much further away from the stars, there were other worlds with an earth in the center and suns and moons turning around this earth. That's what they had in mind. It's quite different from the universe of today. These were their worlds, what they meant by other worlds. So it's strange how people can think about the universe. We can say that today, but they had other ideas in those times. Now, as we all know, the thought of Aristotle, which was encompassing everything, was adopted by the Western world of the Catholic Church for 15 centuries. I mean, he was the person which most affected the Western thought than any other one. And until the Middle Ages, these arguments of a single world, due to Aristotle, were enriched by theological thought, theologians, and Christianity. And one of the greatest thinkers of Christianity was St. Augustine. We thought that the resurrection of Christ was a unique event in the world history. And since it's a unique event, there cannot be other worlds where this could happen. Still, another thinker, Albertus Magnus, thought something that comes always in mind. If God is almighty, why shouldn't he do other worlds? And one of his disciples, another great thinker, St. Thomas Aquinas, thought about that, and the only answer he could find was by, how do you say, in Latin it's reductio ad absurdum, by going to showing some impossibility, saying that something, we assume that it is correct, and then we show that it is impossible. And he said that if God created other worlds, he had two choices, either to make them all similar or all different. All similar is against the divine wisdom. It's stupid to make the same thing many times. If you made different things, some of them would be more perfect than others, and this is against the perfection of the divine act. So, by reduction ad absurdum, there is only one word. Now, these things may make us smile today, but in those days it was very dangerous to play with those things, and this is why you have heard about Giordano Bruno, probably. He was burned at stake because he said that there is an infinite number of worlds. Yeah, infinite. Sorry, it's not, this is infinite here. And so he was burned at the stake. And this was just a few years before Galileo used the telescope and observed that, in fact, yes, the sun was not so perfect as Aristotle has thought. The sun has spots on its surface. Galileo saw the spots, that's why he became blind. He was looking at the sun with a telescope. He saw the phases of Venus. He saw that Jupiter had 4 Galilean satellites, so it was also orbited. The Earth was not, everything was not turning around the Earth, and so on and so forth. So in the Renaissance, Copernicus showed that there is the system of the world is not around the Earth, but rather around the sun. And since then, we think that the Copernican principle, it's also called principle of mediocrity, says that our position in the universe has nothing special. Is not exceptional. And on top of that, Galileo, with his experiments, and Newton, with his theory, showed that in contrast to what Aristotle was saying, the laws of physics are the same down here, up there. There are not different stuff down here and up there. All this is fine. It could point out that life, after all, could also be up there. Yes, but there is a difference, because physics is one thing, and we can check the laws of physics down here and up there. I mean, the constant of gravity has been checked by observations of the light of distant quasars to 10 to the minus, I don't remember how much. But what about the laws of biology, anthropology, sociology, which lead to human intelligence and technology? Can I rule out that They are not applied up there in the same way as down here. And this is a big question. So we don't know yet. Okay, this was a historical introduction. Now, as we know, I go very rapidly because these are facts very well known that we have searched in the solar system. We have not found traces even at the microscopic level. We don't think that in the giant planets there is. Perhaps in some of their satellites. We have looked in Mars. I mean, Julia presented experiments on the surface of Mars. We don't believe in Martians anymore, but we think that there might be some traces of microscopic life in the underground Mars. And some people think that we know that there is liquid water in the oceans behind the ices of Europa, and Europa is one of the biggest satellites of Jupiter, also Enceladus, one of the satellites of Saturn. And there are experiments designed for that. Perhaps they will be launched sometime. But that's all for the solar system. Now, there is another thing we started, and then I'm getting closer to the Drake equation and the Fermi paradox. Now, in '59, radio technologies were very much developed, and the Second World War contributed in that. And two researchers in the United States, Philip Morrison was one of the greatest physicists of that period. He participated in the Manhattan Project with Giuseppe Cocconi, both of them in the Cornell University. They suggested that the best way to search for intelligent life, technologically developed life, was through radio signals. Why radio signals? Because they are not absorbed. You know that most of the stars are in the disk of our galaxy. But the disk of our galaxy, so in principle, we should look in the plane of the galaxy to find civilizations. But the plane of our galaxy also contains gas and dust. And gas and dust absorb the optical wavelengths. So we cannot look with optical telescopes in the disk. We don't see very much of it. We see at most the brightest stars until about 2 kiloparsecs from the sun, which means 5,000 light years. But the galaxy is 40,000 light years across the radius. So radio waves are not absorbed by gas and dust, so you can look far away. And the second thing is radio waves have longer wavelengths, so less energy than the optical wavelengths. So it's more economic to search for information or to emit in those wavelengths. That's why the research for signals is made with radio telescopes, not with optical wavelengths or X-rays or whatever. And what they said in their paper was very interesting. The probability of success looking for radio waves is difficult to estimate. But if we never search, the chances of success are zero, which of course have some meaning. And the rest is history. Frank Drake, a radio astronomer in the Green Bank Telescope in West Virginia, undertook such a program. And preparing the agenda for such a program, he asked himself, okay, but the galaxy is vast, 200 billion stars. Which stars to look for? And then he formulated the famous Drake equation that we heard before. Julia also developed in this morning. I will not go through all the terms in the equation. When Drake formulated it back in 1960, the only thing we knew was more or less the rate of star formation. But we didn't even know at that time whether there were planets or not. Nana presented today what we know about the planets, so the second and the third term of this equation, and all the rest, the other four terms, are totally unknown. You know that there have been also other forms of the late Drake equation. One might ask why only those terms and not some other terms, why it's so important just to pick up life, intelligence, technology. Are there other steps going from life to technology? Yes, there are. Are they important? Perhaps. Some people think they're very important. Of course, you can increase the number of steps and increase also the number of uncertainty. But the basic thing, I mean, of course, I can tell you that the Drake equation has absolutely no predictive power. That's the only thing you have to know. There is no predictive power in that because we don't know the other terms. And when we shall have some idea about the other terms, it will be only when we shall have the answer to the problem. Because to put a value on the fraction of stars that have planets that have life or intelligent life means that we must find such a thing. But then already we shall have the answer before starting doing statistics. Does this mean that the Drake equation is useless? No, it's not useless. It has been extremely useful because it concerned a very important problem that occupied even the ancients. And when you have, but it's also a very complex, complicated problem. We don't, as we heard before, we don't even know what life is. So what do you do when you have a very complex problem? We don't try to solve it all together. You just chop it in smaller problems. And you are trying to find partial answers, hoping that at some point you will have the answers to all the pieces of the puzzle. That's what the Drake equation did, and that's why it is widely used. Okay, I will skip all that, because in the beginning there was a lot of optimism about the search for radio waves. There have been projects, the SETI project in the 60s and 70s. Now, at some point in the 90s, NASA stopped financing those projects, and now they run with private funds, basically, of this guy, Yuri Miller, a Russian billionaire, oligarch. But for the moment, we have not any result. Now, we know there are many planets, and let me now come to the Drake equation. One thing that people should realize is that this Drake equation describes a system which is in a kind of equilibrium. You might ask yourselves why the Drake equation does not contain the total number of stars in the galaxy. We said it's about 100 to 100 billions. And just pick up those that are appropriate for life. Because Drake was interested in a civilization. He was not interested for the first term, just life. If you are interested only in life, in, say, bacteria, we know that bacteria are here on Earth since the Earth was formed, for 4 or 5 billion years. For all practical purposes, they are eternal. But what do you do when you have something, you are interested in something, in that case a communicative civilization, which is not eternal? It has some duration of life. You have to take this into account. It's not the same thing to looking for something which is long-lived and something which is short-lived. That's why the last term in this equation, the duration of the civilization, is the role it plays. So many of you are probably physicists. You know the radioactive decay law. The decay rate is the number of nuclei at some point divided by the lifetime of the nuclei. And if you are in a system of equilibrium, the production is equal to the destruction rate. So the production rate equals n over t. And you can solve for n is production rate times t. And this looks exactly like the Drake equation. The Drake equation describes the system in equilibrium, or in steady state, if you want. The number of communicating civilizations, the product of the first 6 terms, is essentially the creation rate of such civilizations. And the last term corresponds to the death rate, because it's this term which determines how long they last. And this is how the equation becomes homogeneous, because the first term is per year, the last term in years, and in the end, all the other terms have no units, and you get an equation without units. Okay, now let us try to simplify that. Instead of adding terms, let's take the first 3 terms, which were presented before, and incorporate them in an astronomical term. This is the only term where we may have answers, perhaps soon, if we are lucky enough. The other 3 terms, we can incorporate them in a biotechnological term, going from intelligence to technology. And the last term, we leave it alone, standing by itself. So the equation becomes like that. For the first term, we heard, I will give a value. From what we know today, it could be, well, 0.1 per year. But I wouldn't be offended if somebody says it's 2 per year or 1/10 per year. I would probably revise it downwards than upwards from that value. For the second term, this product, we know one thing. We have no idea about its value, but we know this is a product of fractions, so it's bounded from above, from unity. It cannot be higher than unity, it's fractions. And the last term stands alone. Now, what we win by this thing? We can present them graphically. Once you know one term, there is the product of 2 other terms. And you can plot it as a function of the lifetime. This is a logarithmic scale. From 100 years, our technological civilization, radio communicating, is about here. And you can go as far as you like, 10 to the 8 years. And then you can play with this term as a parameter, the biotechnological. Remember, it can be at most equal to 1. So you are bound from above from 1. If you have a life, if the lifetimes are 100 years, you multiply by 0.1, and you have one civilization. You are here, okay? But if you have smaller factors, 100 here, 10 to the minus 4 here, 10 to the minus 6 here, you have these lines. These are straight lines in log-log diagrams. And now, of course, you can get 1,000 civilizations in various cases. If you have a factor equal to 1, then the lifetime is 10 to the 4 years. And if you have 100 times longer life, then you have to reduce the biotechnological factor by a factor of 100. It's 0.01 up there. Okay, this is fairly simple from a mathematical point of view. But it gives us a convenient representation, a graphical representation, to see things, to see what we can expect when we're playing with the values of those factors. If by doing statistics we find that the product of the three factors biotechnologically is 10 to the minus 2, then we should look, 10 to the minus 2 is this one. Then we would know that the lifetime should be across this line there. But now what happens if we have a biotechnological factor which is 10 to the minus 4? And we think that lifetimes of civilizations are only 10 to the 4 years. We are down here, which is below 1. Some people, you will often see that we are bound from below from n equal 1, because we are here. But this is not true, because, of course, we are here. Okay, I'll give you an example. Suppose you have a small village which is abandoned by its inhabitants. And every 1 month per year, one of the inhabitants has kept his house and goes there for holidays. What is the population of that village? It's populated by one person only 1 month per year. If there would be a census there, what would the guy making the census would say? The probability of finding the guy there would be 1/12, 1 month per year. It's below unity. So it's a statistical interpretation of n below 1. It could be here. And you can imagine, well, a civilization which lives for 2 million years, then it decays, destroyed. Then for 10 million years there is no one. And then 10 million years later in the galaxy it appears another civilization, and so on and so forth. So the number n if there were in the Andromeda galaxy people observing our galaxy, they would find either 1 or 0 civilization. But statistically, they would find 0.1. This would be the population statistically of our galaxy. So the answer to the question, are we alone? We may be alone in space, in the space of our galaxy. But it does not mean that we're alone in time, necessarily. We are not the first either. And we are not unique, necessarily. It may well be that thousands of civilizations have appeared in our galaxy before us. And even they became much more advanced than ours. They lived for 2 million years, technologically. And during that time, perhaps they explored their environment. And they found nothing. Because the previous one died 10 million years ago and no traces were left. And they ultimately disappeared. They did not find others. They were unaware of the existence of others. And they could not imagine that others would succeed them. This is, again, one possibility. I'm not saying that this is what happened. But it is as plausible as any other thing that we can say about life and civilization in the galaxy. Because the lifetime of the galaxy is 10 billion years. Is 1,000 longer than the 10 million years that you see there. 1,000 times longer. Okay, and this brings us to the second part of my talk, which is the Fermi paradox. Now, Enrico Fermi, as you probably know, was one of the greatest physicists of the 20th century. He formulated a theory for radioactivity in the late 30s when he was in Italy. And for that theory, he got the Nobel Prize a few years later. And then he went to the United States because his wife was Jewish Italian, and the regime of Mussolini was not very favorable to that. So they immigrated in the United States, and there he was the first to obtain a chain reaction. And so he was a theoretician, he became an experimentalist. And this is quite unusual in physics. He was probably the last great experimentalist in physics. And now in a discussion with colleagues in the Los Alamos laboratory, where the Project Manhattan, he was also part of Project Manhattan. From what we know, because there are no written reports on that, a discussion on possibility of extraterrestrial life, he said at some point, where are they? The point is that we don't know what kind of discussion they have. And even when somebody in the 90s was interested to find the people who participated in that lunch, their memories were quite confusing of who said exactly what and how the discussion evolved. Anyway, this is the only thing we have from that. But this question, where are they, remained unknown for a long time. And in '75, an astronomer, American astronomer, Michael Hart, rediscovered that independently. He wrote a long paper where he was arguing that quite probably there are very few up there, and even it may well be that we are alone in the galaxy. And in that case, the research of extraterrestrial signals is a waste of time and money. And there was a heated debate because in that period, it was a period where a lot of people were developing projects to look for extraterrestrial, for radio signals. And after that heated debate was Carl Sagan who gave the name, the Fermi paradox, to this question. So a quarter of a century after Fermi formulated his question. Now, as usually, then another historical thing, most of the ideas are not new. They do not appear out of the blue. In some cases, other people have asked similar questions, even though they did not have the same knowledge. Fermi knew much more about the universe and stars and galaxies that this guy here, Fontenelle, was a French member of the Academy, but mostly he is thought to have written the first very popular book, at least in France, about the world, Entretien, so discussions on the plurality of the worlds. You see, at that time, the ancient name, the ancient Greek name, plurality of the worlds, was still there. This was the terms of the debate, the plurality of the worlds, Entretien sur la pluralité des mondes. And the book is written in the form of a dialogue between a philosopher and the young Marchioness, who at some point, the philosopher says that intelligent beings exist in other worlds, such as the moon. And the Marchioness said, okay, this is bullshit. In fact, if this were the case, the moon's inhabitants would already have come to Earth. And the only, so you see, it's essentially the Fermi paradox, why they are not here. And the only thing that the philosopher finds to say is that, you know, it's the time needed to master space travel to come from the moon here is probably too long. And if it is greater than 6,000 years, we understand why they have not been here to visit us. Now, why 6,000 years? Because in those days, we are back in the 17th century, the age of the Earth was unknown. And a lot of people who have tried to evaluate the age of the Earth were based on biblical accounts. Many people, including Newton himself, tried to evaluate the age of the Earth by going, you know, from Abraham to Isaac to everything that is listed in the Bible. And they evaluated it, but also Methuselah and other guys were mentioned who have lived 900 years. Methuselah is supposed to have lived 900 years. And the age of the Earth was evaluated to 6,000 years. The situation changed later with thermodynamics in the 19th century when people tried to evaluate the age of the Earth by the cooling time of the Earth. And they found things like 30 million years. This was the standard in the 19th century. Darwin requested longer time scales for its evolution, 300 million years, which looked improbable, and it was only in the early 20th century with radioactivity that we found when the age of the Earth is 4.5 billion years. Now, notice that this is symmetric between the inhabitants of the moon and the inhabitants of the Earth, because both are supposed to have the same duration of 6,000 years. So if they could not come here, they cannot come here because we cannot go there. Today, the Fermi paradox is not symmetric, because we are very young in the cosmic scene. But we know that there are stars that are much older than our sun. So they have a lot of time to come here, much more than we have. So it's not the same thing. Anyway, but other people also have thought about that. One of them was, if there is a name that we have to know about space conquest and astronautics, is Konstantin Tsiolkovsky. Tsiolkovsky was a Russian mathematician who taught mathematics in a place near Moscow, but he was also the guy who thought about propulsion in space. You know, in the late 19th century, Jules Verne sent his astronauts to the moon by a cannon. They put them in a cannon, they send them up there. But this would not work. I mean, the astronauts would be killed by the shock during the acceleration of the launch. And also, they would be killed by the heat developed by the friction with the atmosphere. Tsiolkovsky realized that the only means to move in the space was by the principle action-equal reaction of Newton. You send something behind you, and you are pushed in the other way. That's how rockets are working. So he thought about rockets. He wrote the equations of rockets, the equations of astronautics. But he was much more than that. He was a visionary. He thought that as man expanded over the whole Earth, the human species, by definition, is meant to migrate to the space, to go elsewhere in other stars. As he characteristically said, the Earth is the cradle of humanity, but no one stays in the cradle for all its life. This was one of the famous things that he thought. And for that reason, he became a member of the Soviet Academy of Sciences, and he was very much honored. But he was much more than that. He was a visionary in the sense that he imagined things that the man could do in space. He could use solar energy, which in space is abundant, use the asteroid resources to construct things in space, and many more things. And then he came across a problem, because if human species is meant to go in space, then why others did not do that, and why did not they come here? So you think it's the same Fermi paradox 40 years before Fermi. And the answer that he had given in his book, Dreams of the Earth and Sky, is that we have been set aside as a reserve of intelligence to allow our species to evolve to perfection, thus being something unique to the cosmic community. By the way, this is one of the solutions of the Fermi paradox that we discussed. Because one of the solutions we shall see is that they exist up there, but they do not come close to us. They leave us to evolve in our own pace, to develop our own civilization, and then at some point we shall become able to join the galactic community and provide something unique, what we have done. This was the idea of Tsiolkovsky, and it was a long time before Fermi. And most of you that know Star Trek, you know the famous prime directive of Star Trek. Is there anybody who does not know Star Trek? Yes, I think. So the prime directive is that, I looked at that when I was a child, in the 60s, late 60s, the original one. And, yeah. As the right of each sentient species to live in accordance with its normal cultural evolution is considered sacred. No Starfleet personnel may interfere with the normal and healthy development of value of life and culture. So it could be one solution of the Fermi paradox. Okay, so what is a paradox, in fact? There are paradoxes that exist in mathematics. A paradox is something which looks strange, but under some assumptions. And usually, it turns out that to solve the paradox, you have to drop one or more of the assumptions. They are not correct. So what are the assumptions behind the Fermi paradox? One of the assumptions is our civilization is not the only technological civilization in the galaxy. I mean, Socrates or Plato or Aristotle could not put this paradox in the same terms, because probably they could never imagine that we would go to the stars. And so if they saw people coming here, they would probably think they are gods. And this is what happened many times. But now we think that we are not the only, we can go to the stars. Not yet exactly, but we suppose that we are not the only technological civilization. Then we are typical in every sense. We are not the most advanced, and not the only one desiring to explore and communicate with others. This is the second assumption. Interstellar travel is not very difficult for a civilization slightly more advanced than ours. So some of them surely have done it. And the fourth one is that colonization of the galaxy is not an impossible enterprise. It can take up to 10 to the 8 years. 100 million years is too long, but it's not very long with respect to the age of the galaxy, which is 100 times longer. So if you put together all this, the only answer is that they should be here. But they are not. So where are they? This is the Fermi paradox analyzed. Okay, just a few things. By the way, how much time do I have, Jan?
I think you have like 5, maybe 10 minutes if you want to.
5, 10 minutes. Okay, okay. So I will not speak about means to go to the stars. The whole chapter of what we have thought, how to send people to the stars. Most of those projects were from the 60s, when there was a lot of optimism for space travel. Probably, yeah, one thing we have in mind is that it takes a lot of energy. And the most, what you see there, Apollo Saturn V at liftoff represented 0.5% of the world power. The engines of Saturn V, when it sent the astronauts to the moon, represented 0.5% of the world power in the 60s. For 1 minute, no more than that. The most elaborate project was the project Daedalus in the 70s, made by a team of English physicists. It was based on fusion, thermonuclear fusion. And here you have, as a function of time, the world power in terawatts since the 60s. And you see down here, Saturn at liftoff had 0.5% of the world power. But the engines of Daedalus project, which was not a manned craft, it was a craft which was supposed to be sent to the closest, one of the closest stellar systems, and go through the system of Barnard's star without decelerating, just sending back photographs after 40 years of travel time at 12% of the light speed. So this is the engines of Daedalus used a power much greater, 20 times greater than one that we have in the world today. So if we suppose that our power increases by 1 or 2%, we can master such energies and concentrate, because we cannot give all our energy to one spaceship in a few centuries from now. So if there will be starships that people have imagined, it's not for tomorrow. Anyway, now here there's something we all know about the cosmic calendar. You represent the life of the whole universe in 1 year, and you realize that when the disk of the galaxy was developed, our sun is developed in September, and life appears in October and November, eukaryotic cells, and so on. In the second panel, you have the month of December, and you see the dinosaurs when mammals appear, the 26th, dinosaurs the 25 at Christmas, birds, flowers, and so on. Tyrannosaurus come the 29, 2 days before the new year, and they disappear the 30th, 65 million years ago. And then you have the final, in the final minute, you have the end of the last 50 seconds before New Year. 30 seconds, half a minute, you have the Egyptian civilization. And then for, where is it? Here, 1 second before midnight, Christopher Columbus arrives in America. So you see that in this cosmic calendar, even 100 million years represents 2 days. I mean, here the dinosaurs die here 65 million years ago. So it's not a long time in the lifetime of the galaxy. If you imagine civilizations expanding like that. Okay, this is how the colonization of the Pacific Islands took place. It took 3,000 to 4,000 years, so a time much longer than a human lifetime going to Polynesia. And yeah, okay. So our galaxy, in the last 5 minutes, I will present some work I did on the Fermi paradox to quantify it, because you will never see it quantified. So our galaxy has also a volume. The problem with both the Drake equation and the Fermi paradox is that it does not take into account the fact that we live in a galaxy. The 100 billion stars, yeah, they are not around us next door. They cover a volume, a disk which has a diameter of 100,000 light years, and a thickness which is not big, 2,000 light years. It's razor thin, this disk. But still, it occupies it's a big place. So we have to take into account the dimensions of the disk, because we know that information goes at light speed, and our ships cannot go at light speed, even less. So what I did was to take into account the dimensions of the galaxy. Suppose that there are a lot of civilizations that appear in the galaxy, and they have a lifetime. Let's say here in this example, 1 million years. And they start exploring their neighborhood by sending ships, and there is a wavefront of colonization. And the expansion velocity, not of the ships, but of the front of colonization is 1,000th of light speed. It's not very big, so it's reasonable. So after some point, they will cover collectively a fraction of the volume of the galaxy. These are all the dots you see there, and they have different sizes depending on their age, the time they have spent. Now you can quantify the probability. What is the probability that we have contact? If those dots have covered the totality of the galactic volume, then the probability would be equal to 1. They should have arrived here. So the probability of contact is the volume occupied by those civilizations divided by the volume of the galaxy, which is known. Then you can quantify that. And it depends on the terms of the Drake equation. Essentially, n, the number of civilizations, and L, the lifetime as a technological species. In order to calculate, however, the volume, you need also to make a hypothesis about the velocity of expansion. And you can imagine different things like that. From top to bottom, just 2 civilizations, 10, 100, 1,000. And from left to right, lifetimes small. 10,000 years is quite long. 100,000, 1 million, 10 million, 50 million years. And depending on the velocity, the speed of the velocity and so on, you see that those dots can cover or not the volume of the galaxy. So you can quantify the paradox. But even if you do that, I will have to go very rapidly. In this diagram you saw before, there are regions that are not covered. This is the blue region here. If you have small lifetimes, you have also a small number of civilizations. And then the volume covered is negligible. And then as you go to higher lifetimes, larger number of civilizations, and remember there is also the fraction f of intelligent civilization in this diagram, then the probability increases. And if it, in the yellow region here it's strong, in the blue region it's very weak. So in the blue region there is no paradox. This means that they do not survive long enough, or they do not expand fast enough, or they are not numerous enough. There are very few. Okay, I'll go rapidly through that. I have defined the region of stroke paradox, whatever. So the bottom line is that even if you quantify that, the main thing qualitatively is this one. Something is rare, but what is rare? Life itself, intelligence, sufficiently advanced technology, or sufficiently old civilizations? It boils down to that or that. You can quantify, but it's a combination of those things. How rare one or many of those things are. Now, I guess that everyone here has his own answer to why they are not here. There is a guy, Stephen Webb, who tried to catalog all the answers that have been given over the years. 15 years ago, he wrote a book, 50 Answers to the Fermi Paradox, 50 Solutions. A few years later, he wrote another book, the same book, updated, 75 Solutions. And now he's preparing another book, 100 Solutions to the Fermi Paradox. So you can introduce also your own solution. So where are they? This is my last slide. One of the answers is they are here. They have come in the past, and they observed or even created or assisted our ancestors. You remember 2001, A Space of Odyssey of Kubrick and Clark, how the monolith arrives and infuses intelligence to our ancestors. They are there, but there are several kinds of solutions. One of them is what Tsiolkovsky and Boll said. They do not wish to come, or they observe us from far away, or there is a zoo. These are sociological answers. So I think it's impossible to make sociology of civilizations. We don't know if they exist at all. Then, they are rare. Okay, if there are two civilizations in the galaxy, it's understandable that they are not here. We don't see them. And they destroy themselves, perhaps, so their lifetime is low. That's also what Fontenelle said. And then the expansion is not rapid enough, or even impossible. Interstellar travel is impossible. And this is what Fred Hoyle, a great British astrophysicist, and also Drake himself put in his writings, that interstellar travel is impossible. This was the answer of Drake. So they are nowhere, and we are alone. And we're alone because most biologists think that arriving to intelligence in the evolution is very improbable, taking into account all the extinctions that took place. If you think that when this meteorite hit the Earth 65 million years ago, if it came 2 hours later in its rendezvous with the Earth, the dinosaurs would still be there. So sometimes we are here by chance. We can think that we are here by chance. Okay, so the question is, are they? Not what are they, but are they? And this is what I'm asking. Some people are optimistic, like Clark. In the preface of Space Odyssey, he claims that someday among the stars we shall meet our equals or our masters. But perhaps the answer is given in this cartoon. Sometimes I think that the surest thing that intelligent life exists elsewhere in the universe is that none of us has tried to contact us. So they're intelligent and they stay away, especially if you think of what is happening or what we are doing in our world today. So I have no answer to the Fermi paradox. It could be anyone, and you can also imagine your own answer. Thanks a lot for your attention.
Well, just to comment on the historical introduction, actually, I'm no historian, obviously, but I think it's my personal opinion, not scientific one, that even in ancient times, the idea of inhabitants of other planets of the solar system must have existed. Maybe we have no direct evidence, but heliocentrism existed, although it was not mainstream. And if you take the True History by Lukianos, where he makes fun of the idea, he doesn't take it seriously. But he's writing a space opera about inhabitants of the moon and Venus and other heavenly bodies. It's not a scientific work by any means, but it to me, it suggests that the idea was around at the time. Otherwise, it would make no sense to make fun of it. So I think the plurality of the worlds, like at the times of Fontenelle and others, I think the idea was there, perhaps.
The idea was there because, as I said, the geocentric system of the world was defended by Aristotle, but the atomists did not defend it. And Aristarchus of Samos thought that the sun was in the center of the solar system, not the Earth. So there were different opinions. And this explains what you just said. But the point is, it's very difficult for us to imagine the power of Aristotelic thought. Today, many people think that Aristotle was just a philosopher like the others. No. Until the Middle Ages, most people, if they wanted to say how a fish is made, they did not go to the river to find a fish and describe it. They said, he said that it is like that, because he had written about everything possible. And he had an enormous impact on the thought of those days. But other ideas, of course, they existed. Yes, sure.
Yeah, and even during the Middle Ages, there were people like Nicolas of Cusa, who argued for the plurality of worlds, despite he was a Catholic cardinal, so definitely no heretic. So it was quite interesting times, but of course the mainstream was elsewhere, definitely. Yeah.
Yeah, okay, thank you for a very interesting lecture, and I very much like this approach of this, let's say, volumetric studies. I'm wondering, actually, in the original Drake equation, the lifetime of civilization, or generally how the equation is set, basically assumes that having a technological civilization capable of communication for each planet is a single shot. Yeah? It happens once and never again. If one takes it as a, and actually it does not have to be the case, because already you have a world teeming with life, and then it's quite, I think it's, since we get rid of a lot of obstacles already, so we are basically solving the, if there is any other civilization or any other kind of intelligent life, and even I think even in Earth life, there are quite visible pathways that could have been followed to develop another kind of intelligent life or another kind of civilization then. And I think even the argument with these extinctions are actually, in my point of view, argument for having actually increasing the probability of evolving and re-evolving some say intelligent life. In terms of calculating number of civilizations statistically, obviously it works because then the lifetime is basically the total lifetime of all technological civilizations on that planet, and that these biotech factors would be some sort of weighted average. And then the Drake equation would still work for calculating the average number of civilization in a galaxy. But it makes a very big difference in terms of this, let's say, spreading model, that either by spreading the electromagnetic waves or spreading physical by colonization and exploration and so on. Wouldn't it be maybe more practical to make, so let's say, update of Drake equation to let's say, because in this case the lifetime term has actually have two different meanings. Yeah? Once one allows for re-emerging of civilization on the same planet, then the term must have be redefined. Maybe pre-added with some term like number of times that this happens, and then it can be used as the same number for this, let's say, lifetime of colonizing civilization, for example.
If I understand you correctly, you mean what happens if, instead of supposing that in one planet there is one civilization which lives a long time, we assume that there are 10 successive civilizations which live for shorter time scales.
Yeah, and actually the sum works the same for the average number of civilization in the galaxy, but definitely does not work the same if one calculates the probability that they will meet.
Yes. So from the practical point of view, I don't think that it changes things. If they are, each one lives less time, it will have less time to expand around. And then the next one will start expanding again from scratch.
Exactly.
Then this will reduce.
That's the difference, because...
Yeah, but this will reduce the volume. You will have more civilizations for less expansion volume, because they start from scratch again. Unless they don't start from the same point. If the first civilization expands up to some point, and then subsequent civilizations from those points go further and further away.
Yeah, because it's not the same. If, for example, let's say we have two civilizations, it was visible on these graphs, two civilizations that both live very long, or whether we are just like, let's say, flicking of two civilizations randomly at each point of time, but completely impossible to catch each other.
Okay, you can increase then the number of civilizations, but have shorter time scales. Yes.
So using only this n number in this way does not actually tell us the probability of meeting each other.
No, of course you can complicate your life even more if you want to imagine many things.
Okay, okay.
You can imagine that the civilizations, when they meet each other, they enrich each other, and their speed increases. The expansion speed increases. Okay, it's hard to I think, yeah, you can imagine many things. Sure.
Okay, we have time for one, maybe two questions, and then on our.
I will be very brief. It has been pointed out, and I think it's true, that in such conditions, as you suggest, it would be much more probable to find remnants of ancient civilization during space exploration than to encounter actual aliens. So maybe
sorry, to find remnants
than meeting them in person. So it may be a case for interstellar archaeology.
You mean in science fiction mostly? Yes, I know about science fiction, thanks. This is an interesting question. What would happen, for instance, if our civilization is extinguished? A lot of people, there are even documentaries on that. What of what we have done on this earth will remain for the longest time? How long the pyramids will stay? And you realize that even the pyramids themselves were not for more than 1 million years in the future. So it depends on at what time the others will come to find out what we shall leave. If we put something in space, it's different. Our satellites, they can be eroded, of course, because meteorites and micrometeorites, they are hitting them. But after 1 or 2 million years, I'm not sure how many of them will have stayed up there, because there are also perturbations. It's not clear. So it depends on how soon after the demise of the civilization we shall arrive on their planet to find traces of that. Last question, yeah.
Thank you. Thank you for your talk again. It's your points are very cool. It's very interesting to hear them. So often when we talk about the development of civilization and intelligent life and technology specifically, we talk about technology that is often very similar to us. So like the signals and the communication we are talking about is focused on radio waves and electromagnetic radiation. So we are very limited in the signals we are looking for. And I don't know, have you heard an argument that this would be the most logical type of technology to develop? Or do you think there could be alternative types?
Radio technology?
What, sorry?
What do you see the most plausible?
The most plausible type of technology? Like, should we start looking for gravitational waves? Should we start looking for other types of signals that we are not really searching for right now? Do you have an opinion on that?
Okay, gravitational waves propagate further away than any other signal because their intensity decreases with distance, not with the square of the distance as any other signal. So if those guys are in the Andromeda galaxy and they want to send a signal, they should send, of course, gravitational waves would do the job, but they have to have means that are unimaginable to us to move such masses and to make collisions of black holes. So these could be civilizations far ahead of us. Now, if they are able to move black holes around, perhaps they can find other things like going through the black holes and make time warps and so on and come here. I don't know, it's hard to imagine such developed civilizations. But by the way, the Fermi paradox tells us that time travel should not be possible, because otherwise they should be here, some of them. Unless if they want to observe us from far. That's another thing.
Okay, thank you again, and thank you both.